Hello, in our last video we introduced the Schrodinger equation. In this video we're going to take the Schrodinger equation and start to apply it. We'll start with a re-examination of the nature of the wave function itself and briefly discuss or review the meaning of the wave function. And then we'll look at a simple example of a free particle in a space and the solution of the Schrodinger equation to that particular model. Alright, so first our review. The interpretation of the wave function, the Born interpretation of the wave function, associates the wave function with the probability amplitude and allows us to calculate the probability of finding a particle in a particular region of space. In this circumstance, if we're interested in the probability of finding a particle between 2 points, which we'll call x1 and x2, we simply integrate over the limits x1 and x2. Remembering that we have this psi star psi, which is called the probability density, where psi star is the complex conjugate of the wave function psi. We reviewed that in the last video, so I won't go into that in more detail here. We'll look at a specific example later in this video. That, of course, is one-dimensional space. If we want to look at, for example, the probability of finding it in two-dimensional space, three-dimensional space, etc. In the case of two-dimensional space, if we're looking at trying to find a particle between two x points, x1 and x2, and 2 points y2 and y1, then we have to do a double integral, again, of the probability density. We're integrating with respect to x and y. For example, if we're talking about this situation where we are indicating probability of finding a particle in two-dimensional space, we might be looking at a rectangular region of space, say like this, where we have x1 and x2 on the horizontal axis and y1 and y2 along the vertical here. So when we do this integration, we basically be asking what's the probability of finding the particle in this rectangular region of space. Now let's naturally talk about what if we want to know the probability of finding the particle in all space. Alright, so we're integrating over all space, and in this particular circumstance, depending on our model, it could be one dimension, two dimension, three dimensions, etc. We use a general notation here for all space. We simply show the integral with the volume element being d tau here, this being the Greek character tau. So whenever you see that d tau, that means we're integrating over all space, whatever all space might be defined as for the particular model that we're dealing with. So let's think about this. If we're integrating over all space, the psi star psi represents the probability density, what would that be equal to? What would we get if we were asking the question, what's the probability of finding the particle in all space? Think about that for a second or two. What do you think? Let's rephrase the question. What's the probability of finding the particle somewhere? Well, if the particle exists at all, it's going to be found somewhere. So there's an absolute certainty that we're going to find it somewhere. And in that particular case, the integration would yield 1. This will be an important issue that we'll bring up later, because we must sometimes adjust our wave functions so that this particular integral is true. If we are going to use psi star psi to determine probabilities, then this must be true. So remember that as we move on and we look at specific models and specific applications of our wave function psi. Alright, so that when we talk about this and this interpretation of the wave function, then because we're dealing with probabilities, there are certain conditions that our wave function must satisfy. If we don't satisfy these conditions, then we have a wave function that's not acceptable. The first of these is that our wave function be continuous. Okay, so what does that mean? Well, if we have this particular graph here, if this graph represents our wave function, you'll notice there are no breaks in the curve. This would be a continuous function. We can contrast that with a function where there is a clear break in our curve right here. That's a discontinuity, and that is not an acceptable wave function. We cannot have that as an acceptable wave function. So if we look at a particular solution wave function for the Schrödinger equation, and we get something that has this discontinuity, we know that that's not an acceptable solution. The other thing is that our wave function must be what we call single value. All right, so here's again a graph that's very similar to the one we had above. It's clearly continuous in this particular circumstance. Here's another wave function. So we have two possible wave functions. So the question is, are both of these acceptable? By single valued, what we mean is that at any given point there's only one possible value of psi. So clearly that's the case here in the first one. At any given point there's only one possible value of psi. And let's just simply ask why that's a necessity in terms of the wave function. If we had more than one possible value of psi, that means there's more than one possible probability at that particular point in space, and we cannot have multiple probabilities for a given point in space. So the first one's okay. We look at the second one here, and let's choose this x1 as our point, and you'll notice that we have three values for psi at x1, and that means there are three probabilities for our particle at position x1. That function is not single valued, and because it's not single valued, it is not acceptable. So that's another condition that must be met by all wave functions that we're going to be using to describe systems, molecular systems and atomic systems and particles in general as we look at the quantum nature of things. All right. The last condition we're going to talk about here is that have a finite amplitude over a finite interval, meaning it can't go to infinity over a finite interval. And again, this should make sense because if it goes to infinity over a finite interval of space, that means that the probability density and integration over a finite region of space would be infinity, and we cannot have a probability that's infinite because the overall probability for all space must be equal to 1. So we can't have that infinity over a finite region of space. Alright, so let's look at our first easy model. This is what's called a free particle. Free particle is one that has no potential energy. That means no interactions. Okay, so there are no interactions, no constraints on where this particle can be in space, so it's free to move everywhere. No interactions again, that's key. So if there are no interactions, that means potential energy V is equal to 0. Okay, and so if we look at the Schrödinger equation here, the one-dimensional Schrödinger equation for a single particle looks like this. If V is equal to 0, then we can eliminate this second term, and we end up with an equation that looks like this. So we have a second derivative here in this equation, but we don't have that term V times psi. So now this is a relatively simple differential equation to solve, but again, we're not going to be solving it ourselves. We're just going to look at the solutions. We're going to do a simple rearrangement here. Clearly, if we're just going to simply move the negative h bar squared over 2m term to the other side of the equation, and we end up with this right here. And then we're going to solve it and figure out what psi will be under those circumstances. Okay, so we find that, again, we're not going through the steps of the solution, but if we did that, we'd find that psi is equal to this exponential e to the plus or minus ikx. It can be both. It can be either. Satisfactory solution, where this k term is equal to the 2me over h bar squared, and in fact you'll notice that the square root is that particular term there. So you'll see a connection here, and this might be important to recognize later on when we look at some similar kinds of equations. Now, while we will not make an effort to solve this differential equation, I will ask, and this will be part of the worksheet problems associated with this video, that you show that this particular wave function does in fact solve the equation. The way you will simply do that is take this wave function and insert it back into the equation, taking its second derivative and multiplying things through. So this is something that we'll be working on, both associated with the worksheet for this video and to make sure that everybody's clear on this in our class, to show that this particular solution works. Alright, so we have a function, this mathematical function, which of course at this point you're just asking, what the heck does this have to do with the real system? How does this tell me anything about this free particle? Let's take a look. First of all, it gives us some information about the energy associated with this. If we go back to the equation that we had for K and just simply rearrange that, and let me rewrite this just so that you know where this came from. On the previous slide, we showed that this K was equal to the square root of 2me over h bar squared. Again, where m is the mass of our particle. So that's the solution to our equation, and that shows that we've got this energy equal to this. Okay, so big deal. What does this mean? Well, one thing that's important, and this may not be significant to you now, but when we look at our next model, you'll see why this is important, is there are no constraints on K. K can be anything. There are no constraints on the solution to our mathematical equations that require that K be some certain value. So because K can be anything, that means that the energy can be anything, and that means the energy is continuous, and most importantly what that means, because at this point you know that atoms and molecules and particles typically have energy levels. In this particular circumstance for the free particle, because energy is continuous and can take on any possible value, there are no energy levels. Let me repeat that. For the free particle, with no interactions, there are no energy levels. All energies are possible according to this equation. The next model we look at in the next video will in fact find that that is not the case, and we will have energy levels, and we'll talk about why we get energy levels in that particular circumstance in the next video. Alright, so we have a situation with energy, and that tells us something. What about the wave function? The wave function psi, and let's look at the probability density, which is psi star psi. Remembering that psi can be A can be any value, it's a constant. It doesn't really matter what the value of A would be. To the ikx, I again being the imaginary number, square root of -1, of course. We had talked about that before. And so if we chose psi being equal to AE to the ikx, psi star would be AE to the negative ikx, because when we have an imaginary function or an imaginary component to a function, the complex conjugate changes the sign of the imaginary term. Again, we talked about that in the last video. Alright, so we have psi and we have psi star, so let's look at psi star psi. Psi star psi is going to be equal to the product of these two functions, and so we multiply these together. We're going to get a squared times this, and then using properties of logarithms, you may recall, or excuse me, exponentials, you may recall that when we multiply two exponentials together, then we just simply add the terms. So we're just going to add negative ikx and ikx when we take that product. And of course when we add negative ikx to ikx, we get 0. So this becomes a squared times e to the 0. And of course we know that e to the 0 is equal to 1. So we end up with a probability density of a squared. Okay, and again, remember, a is a constant, can take on any value. And the particular value it takes on is not important here, but what is important is that it's a constant. And you'll notice that that means it doesn't depend on position x. Alright, it's a constant, which means because it's a constant, it's the same everywhere. It doesn't depend on x. So what we find then for our solution to the free particle problem is that there are no constraints on the position of that particle. The probability of finding that particle is the same at every point in space. There's no position that's preferred over another. It can be anywhere, and the probability of finding it anywhere is the same. So, as we noted earlier, we have no energy levels. We note the probability of the particle is the same everywhere. This is the solution to the free particle. Again, free particle has continuous energy. Probability of finding it's the same anywhere. So this is our simple model. In our next video, we're going to be taking a look at a model which has some constraints, and we're going to see how that affects both the wave function and the energy associated with that particular system. And even though it's a simple system, we'll find that there are some connections that will allow us to draw conclusions about larger molecular systems. So we'll begin to see how this stuff applies to chemical phenomena, something that we will look forward to. So stay tuned for our next video on the Schrödinger equation and the simple model of the particle in a one-dimensional box.